Nagesh is not here. Anyways, so let's see. So this problem 4001, there is this n by n array of numbers. Right. So does everybody understand what the question is? So let me just bring what the question is. Right. So let's take a small case. Right. So let's take a 3 by 3 case. Now what are the same? Every row consists of numbers from 1 to 3 in some order. Right. So every row is a permutation of the numbers from 1 to 3. Okay. So for example, let's say the first row is 1, 2, 3. And since n is odd, so I've taken it like this. Okay. And see this condition. Do you recognize what this condition means? Anyone? Aij is equal to Aji. It means that there is some sort of a symmetry, right? So you have the diagonal, there's something here, then there will be this thing will be equal. Okay. But basically Aij is Aji is already written. So for example, what I am forced to put something here. This is A21. Okay, second row, first column. Okay, so what do I have to put there? 2, right? I have to put a 2 there. There's no other choice because this is 2, this is 1, 2, first row, second column. That's how we read it, right? And so that's 2, 1. I have to put it. Now here I am completely free, at least it seems. Do I what can I put there? Well, I'm free to put anything there, right? So let us see. Let us not put anything there so far. This 3 means that this is 3, right? Now, how do you fill the rest of the array? If this is x, then this has to be x. So, what can I put there? Well, apparently I can put anything. But okay, in this one I cannot put 2, right? Because 2 is already there in that row. So I'll put maybe, let's say I put 3. Then this becomes 3. Is it okay? Is it okay?
So there are 2 3s in the last.
Yes. So it's not okay, right? So I am so it seems like I don't have much choice, right? So I have to put a 1 here, and then this one has to be a 1. Well, then this means that this one has to be a 2, and this one then has to be a 3. And this is what they are telling us to prove, right? That on the diagonal, you are going to get all the distinct elements. It's a nice thing, right? Now let us think. So Aparna, just give us a couple of minutes to all of us, because and then you can tell the solution. Okay.
Sir, I didn't read the solution actually, so I tried it myself by
Yes.
a different.
Okay, yeah. No, I mean solution meaning that any solution. Your solution is obviously first you should say if you have. Anyways, we will give us a minute. Currently I don't know if it is true. So it feels true. So is everybody convinced for the 3 by 3 case that it has to be at least? So Aparna, can you explain for the 3 by 3? Okay, let's just do the 2 by 2 case. It will not be true, right? Because it's an even number and they are not asking, so it may not be true. And it's 2 by 2 case. Is it true? No, right? Not. So it's something to do with the odd, because see, this is satisfying all the premises of the question, right? But it is not. What is it about odd? So maybe it's this one, right? Finished.
So for the 3 by 3 case, are we looking at the symmetry diagonally?
Are we looking at the, sorry,
Symmetry diagonally.
symmetry diagonal? I didn't understand. Can you say? No, I didn't understand what you're saying.
Like we said that there's a symmetry because Aij is equal to Aj.
Right.
We are looking at that symmetry like diagonally.
Oh yes, you can say that. It is yeah. Yes. Yeah, like there is a diagonal line, and then anything you have, you just reflect it diagonally, and that you go to AJI. Yeah, that is correct, I would say. Because if you've done coordinate geometry, right, it happens like that. But so for the, so Aparna, can you explain if you have done the 3 by, I just want the 3 by 3 case, if you have done it.
Sir, I'm not sure if the method is correct, but I did it like this, that you have 3 by 3 boxes, and like if you start from the first row, then the first box can be filled with 3 numbers. Like it has 3 choices. It can be 1, 2, or 3.
Right. Okay.
And then the second box will have 2 choices.
Mm-hmm.
And the third box will obviously have the number left, one choice.
Right.
When we come to the second row, then the first box will be equal to the second box in the first row, so that will have only one choice.
Yeah. So right.
As for the rest 2 numbers, so the second box will have 2 choices, and the third box will have one choice.
Okay.
And then similarly in the third row, the first 2 boxes will have the same value. Like you'll end up with one choice, and one choice.
Okay. Okay. Right. These two are same. And okay. These two are same. Right.
So then when we see the diagonal, you'll get 3, 2, 1.
But oh. Why? I don't. Why should they be different? Ah. Yes. Yes. Right. Makes sense. Does anybody see why they have to be different? Like so, this one, this has to be this circle. There is no other way. Right? And this one has to be this stick. There's no other choice. And then that one, not then, that one has to be the cross. There is no other choice. So they do come out to be distinct. And even you see the anti-diagonal, you know what I mean, this one, that is all same. That is also coming out. So this 3 by 3 case is correct. I mean, this is right. But then why will this always be true for the 5 by 5 case? How do we explain? Then we have to bring in the oddness, that it is odd. That has to somehow be used. And I also had a similar reasoning for the 3 by 3 case. Essentially the same idea. Yeah, so the matrix is symmetric, right? So this means one thing though, right? You can see that every column has to also be distinct, right? Like even in the question itself, this already implies that every column has to be distinct because of symmetry, right? So by symmetry, you see that the first row will be same as first column, and second row is same as second column, right? Because that is just symmetry. Second row, second column, right? This gets reflected here, this gets reflected here. Second row and second column will be same. Similarly, third row and third column will be same, right? And you can see that in the picture also we are getting. So it means that the column also have distinct elements. But the symmetry has to give us more. So we get that even the diagonals are all same. And the anti-diagonals are all equal. I mean, diagonals are all different. I mean, 5 by 5 also we can draw a picture and then we can try, but uh,
So what I meant to say was that in the suppose in the n by n case that the first box will have n choices, and then when you come to the second row, the the second box will have n minus one choices, and then when you come to the third row, the third box will have n minus two choices, and like that, in the end you'll end up with one. So you'll have the n numbers in the diagram.
no, that will not. I mean, that you need to have more things to say that. Why? Because yeah, I mean, I understand that the in the end you are saying that the diagonals will have a unique choice, right? Every element, like when you fill the rest of the matrix, then a diagonal, every element in the diagonal will not have more than one choice. I understand that, but you see that was not enough for us to say that they are different. Does everybody notice that, right? Just because the diagonals have distinct choice, it doesn't mean that I can put like make all of them same. There is more to it, and you see in your argument also you're not using the fact that n is odd. Okay, here it is not just that, right? There is the other thing also, that the rest of the rows are kind of different and so on, and somehow odd has to be used. Uh, Hmm. Yes. Are you sure that they are all distinct? The problem is that it's true only for odd numbers. So there is a reasoning which has to work odd. And somehow it will not work for me. I tried a few things, but that don't work. I was trying to say if you have a 5 by 5 case and you have a 3 by 3 block right in the corner, like this. And somehow I was thinking that something, but no, that does not work. If I take this away, the diagonals get polluted. First, second, third.
If n is even, then the diagonals won't have unique numbers.
Yes, that's the problem. Yeah, for 2 by 2 case you can see, right? And so that's why the reasoning has to be something exclusive to this. But hold on, it should not. So it should not be something very complicated. Okay, so let us think something. Let's see. Uh, let us try on the board one. Right? 5 by 5. 5 x1 x. I mean, it doesn't matter. So let's just put 1, 2, 3, 4, 5. Right? That is okay. Let's think, right? Let us simplify the question. Okay, so let's say we are not able to do the problem, right? So let us say if this is 1. We want to say something goes wrong. Right? What would go wrong? This is 1. This one has to be 2. So what would go wrong? And this has to be 3. This has to be 4. So this we cannot complete it to a matrix in the way that is needed, meaning symmetrically and so on. First one. So like if I put a 4 here, put a 4 here. then the 4 will be here. Then that's a problem. But all this is very, very special. Let us see. Yeah, there is something to do with the oddness. Let's do paste 4 in there. Yeah. First, wait. Correct. Okay, that's fine. No, so far I can put the 4 here because there is nowhere else I can put the 4 for the 4th row, for the 5th row, because otherwise it will match with one of the columns. We'll have a repetition, right? But let's see. Now you have to put the 5 there, and then this has to be right. And now what does it mean? It means that the 5 has to be here, otherwise it will not work. Then this one has to be 3, and then it means this one has to be 3. Here I can put a 2 or a 3, but I have to put a 3 there, right? I cannot put a 2. Otherwise, the 3 cannot be placed anywhere else. It cannot be placed in the second and third column. So it has to be there, otherwise the row will not have, this row will not have. Fine. Now the problem is, no, there's not a problem yet. Fine, it seems fine. Then put 1 here, 1 here, put so this is 1, so this has to be 2, and then it has to be 2. Yeah, then there's a problem here. This one cannot have a 2, and also this also, right? Because that row has it. We are getting into a problem, but it's not clear. And so the point is that the 2 is becoming a problem because the 2 should have been on the diagonal, right? And so that is how we have to now use it. Yeah, maybe we can say like this, right? That if so you see the way it's happening is that the 2 is not present on the diagonal and the 2 is creating the problem, right? If we assume that, let's say, the number x is not present on the diagonal, then where can it be? You see, right? So maybe you can keep this diagram as a reference, but don't use it too much. In the sense that use it as much as it gives you the generality of the reason. From here, what I feel is that we have to reason on the element that is not on the diagram, because that is creating the problem. So let's say, it doesn't matter which element, right? Let's say that 2 is not on the diagram. Because see, there are only n numbers, so there are many ways to prove that they are distinct. Prove that every number appears, then they have to appear only once, or whatever. This seems to be the correct way. Let's see. Say 2 is not on the diagram. Then from here we have to say something without relying too much on 5 by 5, so that our reasoning will work always. How many 2's do we need in the matrix? 5 2's, right? think doing it in the wrong way. We need 5 2s. Am I correct? Do we need 5 2s? Right. Every row needs a 2 and every column needs a 2, but that is not 10, obviously. 5 2s. So then why can't we put 5 2s beyond the diagonal? So let's see. I mean, so if you have a 2 in Aij, if we are getting there, right? It seems to work. Think about this. Think about just think about it for a minute. Where will you place the 2s if you're not going to place any one of them on the diagonal? Pragdish, tell me, give me just one place where you would like to place a 2. Any place. Just tell me the row and column number.
Sir.
Yes. Just one second. Yeah. Oh, yes. One second. Pragdish, can you just give me say any place where you want to place a 2? See, we need to place 5 2s. You start with 1, 2, anywhere you want to place.
No, what do you mean? Anywhere in the diagonal?
No, yeah, anywhere apart from the diagonal, right? Because let's say the 2 is not on the diagonal.
Okay.
Where would you want? Just anywhere, just to keep the randomness, I'm saying, so that I am not picking them in the way.
Okay. So no rules, right? Just anywhere
No.
randomly.
Yes, yeah, apart from the diagonal, yes.
Okay, so second row, first column.
Yes, second row, first column, good. And now you see, and everybody sees that now, since I placed a 2 here, I have to place other 2 here. Okay. So we have placed the 2 in first row, second column, and second row, first column. Now let's say I place another 2 here and another 2 here. Yeah. Where will I place the 5th 2? Can I place it anywhere which is not on the diagonal? Anywhere, please answer. Think. Aparna, you were saying something?
Yes, sir. I was saying that apart from the diagonal, if we keep the 2 anywhere on the top or the bottom, we need to keep even number of 2s.
That's it. That's it. And that is the point. Yes. So then you need to keep an even number of 2s, but you need 5 2s. And any odd number will not. This is what we were not seeing in the beginning. The symmetry is forcing you to have even number of stuff outside, even number of copies, right? Now everything looks so simple. We were so stupid. But no, in the sense, you understand, right? If x is not on the diagonal, then you need even number of x's. Right? If x is not on the diagonal, yeah. Right? I mean, I meant to say that, yeah, if x is not on the diagonal, then you need even number of x's because there is a symmetry. If you place x anywhere, you have to place another copy of x. And then, so you need even number. Then you'll get even number, not need, you'll get even number of x's. But you need odd number of x's. That's the problem. And don't go by this idea. Finally, it looks very nice idea, but I didn't come up with it. I did it with you guys. Right? I never knew this question, and I did not use any maths. Just no math, right? It's the puzzle. Look at the process that I am going through. We should do it in better way, faster. But look at the process I am going through. Okay. So let's meet on the other side. Meeting is going to end. Then let's try to solve maybe one more question. Okay. I'm ending the meeting.